Hello everyone, I am Nandini, Department of Computer Science Engineering, Artificial Intelligence from Sri Venkateswara College of Engineering, Bangalore. And today we are going to discuss about my engineering mathematics. The topics are probability, mass and density functions, mathematical expectation, mean and variance of Poisson distribution. First is a probability mass function. Definition. The probability mass function is defined on all the values of R where it takes all the arguments of any real number. It does not belong to the value of x when the argument value equals to 0. And when the argument belongs to x, the value of PMF should be positive. And the probability mass function is usually the primary component of defining a discrete probability distribution. The probability mass function is also called a probability function or frequency function, which characterizes the distribution of a discrete random variable. Let x be a discrete random variable of a function, then the probability mass function of a random variable x is given by P of x is equals to P of capital X is equals to small x. For all small x belongs to the range of capital X. It is noted that the probability function should fall under the condition P of x is greater than or equal to 0 and summation of range of P of x is equals to 1. And here the range of x is a countable set and it can be written as x1, x2 and x3. And let us see some differences between PMF and PDF. PMF solution ranges between numbers of discrete random variables. PDF the solution is in the range of continuous random variables. PMF uses discrete random variables. PDF uses continuous random variables. And applications of probability mass functions. Probability mass function plays an important role in statistics. It defines the probabilities for a given discrete random variable. It integrates the variable for the given random number, which is equal to the probability for the random variable. And it is used to calculate the mean and variance of the discrete distribution. It is used in the binomial and Poisson distribution to find the probability value where it uses the discrete values. And this is a simple example for probability mass function and you can go through it. Probability density function. The probability density function defines the probability function representing the density of a continuous random variable lying between a specific range of values. In other words, the probability density function produces the likelihood of values of a continuous random variable. Sometimes it is also called a probability distribution function or just a probability function. However, the actual truth is probability density function is defined for continuous random variables and whereas probability mass function is defined for discrete random variables. And the formula for the probability density function is P of capital X is greater than A and smaller than B, that is equals to integration of f of x is equals to dx. Or P of capital X is greater than or equal to A, smaller than or equal to B, that is equals to the integration of f of x into dx. And this is a graph for the probability density function. The probability density function is defined as an integral of the density of a variable density over a given range. It is denoted by f of x. This function is positive or non-negative at any point of a graph, and its integral, more specifically the definite integral of PDF over the entire space, is always equal to 1. And the graph of PDF typically resembles a bell curve with the probability of the outcome below the curve. And we can see here the graph which is in the shape of the bell. Applications of probability density function. In statistics, it is used to calculate the probabilities associated with the random variables. And the probability density function is used in modeling the annual rate of atmospheric NOx temporal concentration. And it is used to model the diesel engine combustion. Probability density function properties. For continuous random variable that takes some value between certain limits, say a and b, the PDF is calculated by finding the area under its curve and x-axis within the lower limit a and upper limit b. The probability density function is non-negative for all the possible values. That is, f of x is greater than or equal to 0 for all x. The area between the density curve and the horizontal x-axis is equal to 1. And this is a simple example for probability density function. Mathematical expectation. Probability is used to denote the happening of a certain event and the occurrence of that event based on the past experiences. The mathematical expectation is the events which are either impossible or a certain event in an experiment. Probability of an impossible event is 0, which is possible only if the numerator is 0. And the probability of a certain event is 1, which is possible only if the numerator and denominator are equal. And it is also known as the product of probability of an event occurring, denoted by P of x, and a value corresponding with the actual observed occurrence of the event. The mathematical expectation is denoted by the formula E of x is equals to summation of x1 p1 comma x2 p2 so on up to xn pn, where x is a random variable with the probability function f of x and p is the probability of the occurrence and n is the number of possible values. Properties of expectation. E of x plus y is equals to E of x plus E of y, and E of xy is equals to E of x E of y. E of a plus f of x is equals to a plus e of f of x, and where a is a constant and f of x is a function, and e of a of x plus b is equals to e of x plus b, where a and b are constants. E of summation of ai xi is equals to summation of ai into e of xi, where ai, that the value for the I is 1 to n are constants. And this is a solved example for the mathematical expectation. The question is, what is the expected number of coin flips for getting two consecutive heads? Let us see the solution. Let the expected value of a coin flips be x. If the first flip is tail, then the probability of the event is 1 by 2. Thus, the total number of flips required is x plus 1. And if the first flip is head and the second flip is tail, then the probability of the event is 1 by 4. And the total number of flips we require is x plus 2. If the first flip is head and the second flip is also head, then the probability of the event is 1 by 4. And the total number of flips we require is 2. By adding this equation, we get x is equals to 1 by 2 into x plus 1 plus 1 by 4 into x plus 2 plus 1 by 4 into 2. By solving the equation, we get x is equals to 6. So the expected number of coin flips for getting a two consecutive eggs is 6. Poisson distribution. The Poisson distribution is a discrete probability function. That means the variable can only take specific values in a given list of numbers, probably infinite. A Poisson distribution measures how many times an event is likely to occur within X period of time. A Poisson random variable X defines the number of successes in an experiment. This distribution occurs when there are events that do not occur as the outcome of a definite number of outcomes. Poisson distribution is used under certain conditions. They are the number of trials n tends to infinity, probability of success p tends to 0, then np is equals to 1 is finite. Poisson distribution formula. The formula for the Poisson distribution function is given by f of x is equals to e of minus lambda and lambda to the power x, that is divided by x factorial, where e is the base of the logarithm and x is a Poisson random variable. Lambda is an average rate of value. Poisson distribution, mean and variance. Assume that we conduct a Poisson experiment in which the average number of successes within the given range is taken as lambda. In Poisson distribution, the mean of distribution is represented by lambda and E is constant, which is approximately equal to 2.71828. Then the Poisson probability is P of x comma lambda is equals to E of minus lambda to the and lambda to the power x divided by x factorial. In Poisson distribution, the mean represented as E of x is equals to lambda. For Poisson distribution, the mean and variance are equal. It means that E of x is equals to V of x, where V of x is the variance. And some of the applications for Poisson distribution are the number of deaths by arse kicking in the army of Prussian, and birth defects and genetic mutations, rare diseases like leukemia because it is very infectious and not so dependent mainly in legal cases, car accident prediction on roads, and traffic flow and the ideal gap distance between vehicles, and number of typing errors found on the page in a book, earphones in a McDonald's, hamburgers, and the spread of an endangered animal in Africa, failure of a machine in a 1 month. And example for the Poisson distribution is a random variable x has a Poisson distribution with a parameter lambda such that p of x is equals to 1 is equals to 0.2, p of x is equals to 2, find p of x is equals to 0. The solution is for a Poisson distribution, the probability function is defined as p of x is equals to x is equals to e of e to the power minus lambda, lambda to the power x divided by x factorial, where lambda is a parameter given that p of x is equals to 1, that is equals to 0.2. P of x is equals to 2, e to the power minus lambda to the power lambda to the power 1, then divided by 1 factorial. The value is 0.2 into e to the power minus lambda, lambda to the power 2, and divided by 2 factorial. Then lambda is equals to lambda squared by 10, lambda is equals to 10. Now substitute lambda is equals to 10 in the formula. We get p of x is equals to 0, is e to the power of minus x and e to the power lambda to the power 0 divided by 0 factorial. P of x is equals to 0, lambda to the power minus 10, we get the value 0.0000454. Thus the p of x is equals to 0, the value is 0.0000454, and this is the example for Poisson distribution. And thank you for watching. Please do like, share and subscribe.